Alright, in this lesson we're going to start talking about prediction and prediction equations. The scatter plot that you see there represents Vegas forecast scores and actual scores for the NFL for the 2007 season. You can see that within this scatter plot something new has been added. Firstly, a couple of lines have been drawn through the scatter plot, and as it turns out, each of the equations that you see here is a prediction equation, and they have done two of them, as it turns out, one for home, one for away. Now, this is not something that I'm particularly interested in, but I found it and I thought it was interesting to show you, lots of different folks might use what we're going to be talking about in this lesson. So let's start talking about prediction. Prediction implies estimating future performance, such as college GPA, from knowledge of current score or standing on some measure, such as SAT. So that's probably somewhat intuitive. The thing I want to point out, though, or emphasize is the fact that you really would not want to try to predict y from x unless you have two variables that are highly correlated. Your R can indicate some ability of x to predict y, but it doesn't tell you how to make the prediction. So that's what we're going to be talking about in this lesson. Now this next slide introduces you to one new friend. These friends actually are old friends. We've been talking about x as the independent variable, y as the dependent variable. A new name for x, though, is predictor variable. A new name for y is a criterion variable. Kind of a new friend, though, is our predicted score on y. So I will say these as either y hat or y prime. It looks like a y apostrophe. Before we move on, I want to give you a little bit of an example of how this might be used. Again, I'll kind of use the NFL. Let's say that NFL teams who spend lots of money trying to figure out who their team needs to draft has been keeping data between NFL success, and they define that as years in the league, and broad jump score. And so for 10 years they've got hundreds and hundreds of athletes that they've kept track of, and they found out that there is a 0.75 correlation between broad jump score and success in the league or years in the leagues. And they decide to try to predict future behavior, future success of this year's draftees by just looking at their broad jump score. Now, if that number were actually correct, it might behoove them to do that, because if you think about the time and expense that they go to try to figure out who to draft, it would make sense that if one variable could predict future performance, they might save lots of money and time. All right, so let's start looking at a regression, what's called a regression line. A regression line is the line that is placed within the scatter plot, and right now we're just going to eyeball that, and it is used for predicting future performance. So if someone came in and they scored here on our x variable, we would go up the line to our prediction line, our regression line, and then over to the y-axis, we would say that's the performance we would expect for you on y. Now, unless r is perfectly +1 or -1, we will not be able to predict with 100% accuracy y from x. Now, again, our eyeball is pretty good, but it's not the best, so we do need something that is more accurate, and I'm going to call that our regression or prediction equation. The regression or prediction equation puts the line in the best possible position on the scatter plot. So here is the general form of the regression equation. Y prime is equal to beta naught plus beta 1 times x. Beta naught, or beta sub 0, is the y-intercept. It's the value of y when x is 0. It tells you where the line actually crosses the x-axis. And then beta 1 is the slope, and it's an indication of the flatness and the direction, the shallowness, the steepness of the line. Most students are somewhat familiar with this, and they know it as the rise over the run. Now, in the next lesson, we will talk about how do you actually calculate beta naught and beta 1 and get that line in the best position possible. So again, right now I'm going to draw it kind of using my eyeball. But let's say that I didn't use my eyeball, I used something like SPSS, and that is the best place for our prediction line. The next concept that you need to have a little bit of a feel for is something called error. And error, by definition, is how different are each of these observed y's from that prediction line. So I'm just going to mark a few. Again, unless r is 1 or minus 1, this line is never going to perfectly predict our behavior. So I'll draw a line over here and say that this is y minus y prime. And again, oops, it should go on the inside. That is the error for a particular score. Now, when we take those errors in combination for every one of the scores, we can calculate something called error sums of squares. Error sum of squares says find the distance between each of these raw scores, these y scores. So there's our distances. We're going to take each of these. So I want to just draw the line to one of them. So that's y minus y prime. And then error sums of squares says take all of those, square them, and then sum them up. So that concept shouldn't be anything that is particularly new to you. What you need to know is that when the line is not eyeballed, okay, we do use our beta naught and beta 1, and we've calculated them. Again, we'll learn that in the next lesson. When the line is not eyeballed but is put in place according to beta naught and beta 1, the error sums of squares is as small as possible. Another way of saying that is that if we put the line anywhere else, we would increase our error sums of squares. All right, so any one of those error scores, y minus y prime, is just by definition an error score, but when we take them in conjunction, we square each of them, we sum them up, we have calculated something called error sums of squares. When the regression line is, and I have in quotations correctly because we'll define that a little bit later, but when it is positioned correctly, our error sums of squares is as small as possible. And that's really the goal of calculating our prediction equation. Okay, when the line is put in place correctly, it is called the line of best fit. So it is the line that best fits the actual scores and minimizes error sums of squares. And I'm going to, in this one, and I would suggest you do this. A while ago I was given the example where someone came in, they scored here, and they would go over there and say, this is your y score. But the reality is once we've calculated beta naught and beta 1, this becomes this. So we wouldn't have to have a scatter plot, find where they scored on the x-axis, move up to the line, and then move over to the left. When someone new came in, we would just put their score here on x after we measured it, and we would calculate what their predicted score on y is. So that line is the line of best fit. It is put in place by the regression equation. It is put in place correctly so that we reduce error sums of squares to the smallest amount possible. All right, the last thing we're going to talk about sort of related to this is something called the least squares criterion. And this will probably bring everything together because I've been using the term eyeballing the line or put in the scatter plot correctly. when we do calculate the values for beta naught and beta 1, that is when we know exactly where the best position for that line is. Because of that, beta naught and beta 1 are called least squared estimators, or LSEs. Beta naught and beta 1 are least squared estimators because once they are calculated, they're what put that line in the best place. Much better than what our eyeball will do. So beta naught, beta 1 put the regression line in the place so as to reduce the error sums of squares to as small as possible. Another way of saying that is that if we put the line anywhere else, we would increase the error sums of squares. So again, I'm eyeballing this, as you know, and here's all of these error scores. Okay, and we know that if we took each of these, squared them, summed them up, for this set of data, that would equal to error sums of squares. I'm going to change colors of pens here, and let's say that I decided I was going to put the line there. That was, I made a mistake, and that's where beta naught and beta 1 told me to put the line. Well, look what happens to the error here. See how far off these points are now? Again, if you took the distance of each of these blue lines, squared it, and then summed it up, that would be considered our error sums of squares, and I can guarantee you by putting that blue line in place, the error sums of squares for this data would be much higher than if we put the line in the place that the correct beta naught and beta 1 told us to put it. So because of that, beta naught and beta 1 are considered least squares estimators. Here's a little joke. My husband would say, "This is me, the nerd. This is my least squared solution." And perhaps there's some of you in here that maybe are in rock and roll bands and you're not square because you're in the band. Okay. This next concept, kind of listen to it. This is a PowerPoint you might need to go back and look at. But I wanted to introduce you to the concept of the regression line as a running mean. And to do that, I'm going to draw a picture here in this big open space. And we're going to say that, that's not very straight. We're going to say that our x-axis is SAT scores. Our y-axis is college GPA. And so like somewhere in here is a college GPA of 1, somewhere in here is a college GPA of 2, somewhere in here is a college GPA of 3. And what we're going to identify on here is an actual mean of this set of data. And so let's say that that actual mean is something like 2.57, the actual freshman mean, all right? And that's what we're calculating here. That's what our y variable is. Somewhere in here, we have our regression equation. Has put our line right there. And I want to introduce you to, again, the concept of that prediction line as a running mean. So we're going to identify this, beta y hat, y prime is equal to beta naught plus beta 1 times x. And let me identify some SAT scores. So this is a SAT of 425, and I don't know, to be honest with you, if these are realistic SAT numbers, so if they're not, forgive me. All right, so let's look at what we've got here. If we're looking at x of 650, let's say that the y prime would be right at 3.0, or maybe let's call it a 3.1. It's a running mean because what's actually is there, this will be a little bit hard to draw, but we're going to pretend this is a mean of a distribution of possible y scores at this x. For a SAT of 425, let's say that that is something like that. So it looks like it would predict a freshman GPA of, let's call that 1.8. Again, what you need to do is draw a little normal curve here, because there's actually a distribution. That's not a very good picture, but there's actually a distribution of possible scores for an x of 425. Okay, so let's kind of review this, and you might want to jot a few notes down. For x equals 650, y prime equals, what do we say, 3.1. That 3.1 is the best estimate of the mean of the distribution of possible GPAs at that SAT score. So I'll say that again. For x equals 650, if we decided that y hat was 3.1, or that 3.1 is the best estimate of the mean of the distribution of possible GPAs at that SAT, at the SAT of 650. For x equals 425, y prime is equal to, what do we say, 1.8. That 1.8 is the best estimate of the mean of the distribution of possible GPAs at that SAT score, at the SAT score of 425. Okay, so that may be something that you need to spend some time letting it sort of soak in, because what we're saying is that unless r is equal to 1, if someone scored 650, we would predict a y prime of 3.1, but that's just the mean of all the possible scores. So it's likely that we may have 2 or 3 people that come in and score 650. You know, one of them may have a GPA out here, one of them maybe have a GPA up here, but that 3.1 is just the mean of the possible GPAs for anyone that scores 650 on the SAT. So from that perspective, our prediction line is considered something like a running mean. All right, I want to spend a little bit of time talking about the slope. I wish I could say that that's me snowboarding, but the truth of the matter is I ski, I don't snowboard, and that looks pretty steep. That's a pretty steep slope. So I want to give you a different definition of the slope other than the rise over the run, which again, mathematically, most people are pretty comfortable with that interpretation of the slope. So our interpretation in this data, if x is equal to, again, SAT scores, y is equal to college GPA, and let's say we do the math and beta 1 is 0.0021, our interpretation is that for every point increase in SAT score, college GPA goes up on average by 0.0012 units. Now, why did we say go up? I said go up, or increases, because in this case, my slope is a positive number. So even though there's not a plus out there, it is a positive number. Can you have a negative slope? Absolutely. So if you have a negative slope, the interpretation would be for every unit change in x, y goes down on average by whatever the units of the slope is. So you can't have a negative slope. Why did I say on average? Again, it's because of the previous slide. Think about it again as the prediction line as being a running mean, right? So that regression line serves as a running mean for possible scores at any given x. All right. So let me give you another example. Let's say x is height, y is weight, and we do some math and conclude that the slope of this prediction equation is 7. What that would say is that for every inch increase in height, weight goes up on average 7 pounds. Okay, so you're going to be doing some homework where you're going to be asked to actually calculate prediction equation and then also interpret the slope. So there's your interpretation of the slope. All right. Now let's move on and talk about how do you use a prediction equation, and how you use it is right here. The unfortunate thing is the picture I had drawn in my notes for that running mean didn't really make it up quite like the real deal. So my drawing was off, but this is actually, I think, some data that was collected. So if y prime is equal to 1.42, that's our beta naught, that's our y-intercept, plus 0.0021 times x, and someone comes in and they scored 650 on the SAT, what is y prime? And that's just a plug and chug. So the 650 times 0.0021 plus 1.42 yields a predicted score of, a predicted GPA of 2.78. Here's the other example. Again, my drawing was not very good at all, but hopefully you got the point. If y prime is equal to 1.42 plus 0.0021 times x, and x is 425, what is y prime? So 425 times 0.0021 plus 1.42 gives us a y prime of 2.31. So again, the way that you use this is someone new comes in, they score whatever they score on the SAT, you plug their SAT score into your prediction formula, and that yields you a predicted GPA. Now, how good is our prediction? How good is the prediction for 650 of a GPA of 2.78? How good is our prediction of a SAT score of 4.25? Y prime being 2.31. Well, good news is that there's a way to actually measure that, and the way that we're gonna measure that is by calculating something called the standard error of estimate, or the standard error of prediction. But it is a mathematical calculation. We'll talk about that in another lesson about how it is actually calculated, but it is an indication of how the degree of imprecision in our estimate. The symbol for that is SY dot X, okay, the standard error of prediction. Basically, what you need to start grasping hold of, and I know this is true because we're going to be talking about this in the last two modules. Any standard error is a form of a standard deviation. So the standard error of prediction is the standard deviation of actual y scores about y prime. And probably the best thing for you to think about is the bad graph that I just drew. But remember, if we said someone scored 650 and we predicted a score for them, that predicted score is just the mean of all possible predicted scores. So we could have, in essence, drawn the 3 standard deviations above and the 3 standard deviations below the mean of that sideways distribution. So again, think about the standard error as the standard error prediction as the standard deviation of that sideways distribution at x equals 650 and at x equals 425. Okay? All right, so in another lesson we will talk about how do you actually calculate that. On the next slide we're actually going to talk a little bit about how do you interpret sy dot x, and what I want you to remember is if we were to go 1 standard deviation above the mean, 1 standard deviation below the mean, so plus or minus 1 standard deviation, we would encompass about 68% of the scores, assuming we're working with a normal distribution. So we're going to use that 68% in our interpretation. So here's our prediction equation again. Or not prediction equation, but our predicted y score. If y prime is equal to 2.78, and we did some calculations and calculated that sy dot x is 0.45, how good is our prediction? Here is the interpretation of sy dot x. The interpretation is that 68 times out of 100, a person's true score on y would not be more than 0.45 units from the predicted score of 2.68. So let that sink in for a moment. 68 times out of 100, a person's true score on y would not be more than 0.45 units from the predicted score. So again, this is a form of a standard deviation. Again, you're going to have some homework where you're going to be asked to calculate standard error prediction and then interpret it. So you might want to have this handy. All right, we're almost through with this lesson. We just have a couple of other little topics I want us to talk about. And the last one actually is regression and sums of squares. Think back to when we were at the end of Module 1, and I had you go in and calculate the mean and standard deviation of 4 different groups of people. As I recall, there was one that was some medicine, and there were different levels of the medicine, and then there was a placebo. And then you listened to one of the Link to the Future lessons, and you learned about partitioning total sums of squares. And remember, the situation that we were in when we were doing that was that instead of considering those 4 groups separately, we wanted to ask the question, was there a statistical difference between the 4 groups? And to do that, we have to partition total sums of squares, and so we start out with all 4 of those groups as if they were in one large group. So it's kind of similar to what we're doing here. So by definition, sums of squares total, and as it turns out on the next slide, we're going to have some graphs, and I'll be drawing kind of some of this for you. But as it turns out, total sums of square is how different is each y from the average score for the data. And so remember when I was drawing my really bad graph, I put the average score on there, and because you should know the average score. So from a conceptual formula or conceptual thought, I guess, this will be how different is each score from the mean of the data. And because we're talking about sums of squares, remember we're going to square this and sum it up. All right, so SS total, how different is each y from the average y score? It's kind of like calculating deviation when we were conceptually calculating standard deviation. Deviation from the mean squared and then summed up. Okay? The sums of squares due to regression, also known as explained variation, is how different is each score, or excuse me, how different is each y prime from the average score. So again, I'll kind of write this in a little formula form that might make it a little bit easier. So how different is each predicted score from the average score? And if we do that for every score, square them and then sum them up, mathematically we could calculate our regression sums of squares, or SSR, or also again known as explained variation. So by definition, if you want to write this down, SSR is the variation that we can account for because we know X. It is the variation in Y, or some of the variation is Y in Y is explained because we know X. So think back to R square. It's kind of like this is the overlap between X and Y. So it's considered explained variation. The variation that we can account for because we know X. All right? And then the last one is sums of squares due to deviation, also known as unexplained variation. By definition, it is how different is each score from its y prime. And another label that you already know for this is that's called error. So look back at those PowerPoints in just a few minutes, but how different is each score from its predicted score? Again, if we squared each of those and summed them up, we would label that unexplained variation. Again, it's maybe kind of a formal definition, if you will. SSD is the variation that is not accounted for by knowing X. It is the unidentified variables that are related to GPA other than someone's SAT score. So again, it's the variation that is not accounted for by knowing X. It's the unidentified variables related to GPA other than SAT score. Okay, so let's take a look at this pictorially. So that might be somewhat helpful for you. This first one we're going to say is our SST. So we'll draw an average score on here. We'll put our prediction line, our prediction equation in there. And this is how different is each score from Y bar. Okay, and so this is our sums of squares total. So everything below the mean has a line drawn up to the mean. Everything above the mean goes down to the line. Everything below the mean comes up. So this is SST. How different is each score from its mean? Very similar to deviation from our first lesson, or lessons. All right, let me put the mean back in here. Here's our prediction line. And this is going to be SSR. This is how different is each Y prime from the mean. So basically everywhere there is a dot, there's going to be a line going up to the mean. And I say dot, probably I should have said that a little bit better. Everywhere that there is a pair of observed scores is really more correct. Okay, so this is SSR. Okay, and I'll come back over here and write this conceptually. This is Y prime minus Y bar squared and summed up. And then lastly is our old friend error. Again, I'll go ahead and put the mean in here, even though it doesn't really play a role here. That is how different are each of the scores from their predicted score. So everything above that prediction line comes down to the line, everything below goes up to the line. Again, this is SSD. These are the things that we cannot account for. So this is how different is each score. Add Y prime in there, squared, and then summed up. All right? And what we're going to see when we do some math with this is that SST is equal to SSR plus SSD. And this is going to kind of be a long formula, but hang in there with me. Y minus, so SS total is equal to Y prime minus Y bar squared plus sum of Y minus Y prime squared. Again, we're going to look at some math where we will kind of prove this to you, if you will. Now, what you need to do is go into those three correlation problems and do step 3 of correlation 1, correlation 2, and correlation 3. Again, don't be shy about coming back and re-listening to this. There may be some of this that's a little fuzzy, so no worries if you need to come back and re-listen.